recording as well, because this talk will also be on our YouTube channel. Do check them out if you missed a couple. Maybe that one was already uploaded. The stage is yours.
Thank you. So can you see my screen?
Yes.
You can, great. Okay, so thank you everyone for coming. This is a very exciting subject, at least for me. I work on black hole astrophysics, and I want to give you a very brief summary or overview of this field research. I want to give some credit to Avi Loeb and Delphine from some of the presentation slides that I will be showing. So here, in this front slide, I'm showing you a galaxy. You can see the dust obscuring the galaxy along the line of sight. You can see that at the center, there's a supermassive black hole at the center, which is ejecting these relativistic particles that you can see in radio and X-ray emission. So it is clear that I will show you later that you can observe these objects at the centers of galaxies, which are responsible for the most powerful radiation seen in the universe. So it's a very interesting field in astrophysics. So the story begins in 106 years ago, when Albert Einstein wrote down the famous Einstein's equations, which describe how space-time evolves. So it specifies how space and time evolve, how geometry describes the universe. And so they are very complicated partial differential equations, a system of differential equations, which are difficult to solve. People thought that it would be nearly impossible, maybe impossible to solve it. But only 1 year later, Karl Schwarzschild, who was a professor in Potsdam, director of the University of Potsdam, wrote down the solutions, in fact, to these equations, as I will show you. And so he basically solved Einstein's equations exactly. And this is now known as the Schwarzschild solution. So he could solve the problem within 1 year. It was during the time of the First World War in 1916. And Schwarzschild solved, after solving the equations, sent a postcard to Einstein telling him about the discovery. But unfortunately, after this solution, Schwarzschild died in the First World War. By the way, Schwarzschild was a big patriot, while Albert Einstein was a pacifist. So unfortunately, Schwarzschild didn't live to go on and explore further this theory. So the summary is that if you are working out the full consequences of a theory, it is for an extended period of time, one is better off being a pacifist. Okay, so here's the black hole, a schematic diagram of a black hole. So the solution of the equations which Schwarzschild showed was that there's a region in space-time where nothing can escape, not even the light can come out. But if you're outside of this region, and you're shining a light bulb from some point, then the photons which are going radially outwards can escape. The ones which are going inwards will be absorbed by the black hole. And there are these interesting light rays which are significantly curved by the space-time around the black hole. So it's interesting that if you're standing here above the black hole, say you have a rocket and you're levitating at this point, and you're looking straight in one direction, and then you can see yourself. There's a photon, or there's a light ring where you can see yourself, your back, as the photons travel around the black hole. So the region where you have the horizon, you can calculate, which is known as the Schwarzschild radius. It's 2 times the gravitational constant times the mass of the black hole divided by the speed of light to the second power. And so if you have a cloud of particles, they will fall in. That's another solution to Einstein's equation. If you have a dust medium of dust which falls in spherically, the particles fall to the center and they form a singularity. So at the very center of this solution to Einstein's equation, the solution actually breaks down, because at that point the curvature becomes infinity. So this shows that the theory, Einstein's theory of gravity, is incomplete, because it cannot be correct at the very center of a black hole. But fortunately, the space around the horizon is well behaved, and so we can use it as an approximation, at least, to nature. So here's another interesting image, which is from the movie Interstellar. So you might have seen it, when which showed nice images for if you go in a spaceship and approach a black hole. And here's a gas cloud which is orbiting around the black hole, and it seems to be warped. But this is just an impression due to the fact that the light rays are traveling on curved trajectories. So even though the disk, that you have a flat gas disk orbiting around the black hole, it seems to be as if it was curved like this. You can also see that one side of this cloud, or of this disk, is much brighter than the other one, because it's Doppler beamed in your direction. So the radiation is beamed at you. And it's also bluer, and there's a redshift in the opposite side. So this is how a black hole would actually look like if you solve Einstein's equations. But you can now actually make pictures with telescopes, as I will show you. But why study black holes to begin with? So there are many exciting reasons to do so. One is in search for the theory of everything. The last step is to combine gravity and quantum physics. So this is the last step, because quantum physics has been unified now. So the electromagnetic interaction has been unified with the weak interaction and the strong interaction. So there's a single theory which can describe fundamental physics, but gravity has not been incorporated in this theory. And to solve this remaining problem, you should really understand how space-time works at the smallest scales, which is relevant, which is the case when you have a very strong region of gravity or very small scales, which are the case for a black hole space-time. And they are also important in astrophysics. Black holes are important in astrophysics. It turns out that in galaxy evolution, they play a crucial role. So there are these supermassive black holes which regulate the growth of galaxies. And you can observe interesting correlations between the large-scale structure of the galaxies, such as their mass and the mass of their dark matter halos, numbers of globular clusters, and so on, and the central supermassive black hole. So somehow, supermassive black holes can regulate how galaxies grow. And they can do so because they can create the most luminous radiation observed in the universe, as I will show you. So basically, it's ironic that black holes are are black, so nothing can escape from inside of them. But if matter is falling into the black holes, then before falling below the horizon, this matter can shine actually extremely brightly. And finally, there's also a new frontier. There's a new method of observing the universe now, which are due to the discovery of gravitational waves. So I will discuss this again. So gravitational waves are produced by black holes, and it gives you an opportunity to study space-time. And of course, it's just fascinating science. So curved space-time allows interesting things for the future. So you basically have this theory, which is described by Einstein's equations, and you can solve these equations. And it turns out that there are these solutions to these equations which show that that time travel, for example, is theoretically at least possible. So this means that you can imagine configurations where you have these trajectories in space-time along which, if you travel, then you can get back to the earlier positions in time. So you can basically travel backwards in time according to general relativity, Einstein's equations. You can also travel forward in time, and that's much more easy. So even in free space, you can just, if you travel to a large high velocity and accelerate to a high velocity close to the speed of light, and then return to the same point in space, return to Earth, for example, you will have traveled forward in time. So you will be much younger than your relatives after you return. So maybe in the future you can use this to construct time machines. It's one of the future possibilities which people can think about. And finally, another motivation is that black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements in their construction are our concepts of space and time, as Chandrasekhar said. And at the same time, in all cultures studied, the single most important criterion of human beauty and attractiveness to the opposite sex is symmetry of the facial features. So by this idea, you can consider black holes to be the most beautiful creatures in the universe. Okay, so let me briefly introduce to you what black holes actually are. So to do this, we need to consider coordinate systems in space-time. So we're plotting one dimension of space-time, of space here on the horizontal axis, and we're plotting time on the vertical axis. And the particle, which is moving in this space-time, in space, can be plotted as a curve in the space-time. So in empty space, these coordinates are just straight lines, and if a particle is at rest, they would just go along a straight line vertically here at constant x, for example. Light rays, on the other hand, follow 45-degree lines. They go with the speed of light, so they can go to the right or to the left. So their trajectories will be described by x equals u plus c times t, where c is the speed of light, or v minus c t, where u is a constant and v is a constant. So it turns out that you can describe space-time just as well by specifying these coordinates u and v instead of x and t. So you're basically switching from this grid shown here to this other grid shown here. So if you specify your points along your trajectory, your u, v coordinates, then you have specified your trajectory completely. And it turns out that it's useful to use these light rays to define your coordinate system. especially if space-time is not empty, but if it has matter in it, such as in the case of a black hole. So to continue, so now we can define in general curved space-time the same type of coordinate system. So you follow the light rays going one way and the other way, and it turns out you can always define your coordinate system such that you can represent it as 45-degree lines, straight lines, with these parameters being constant, little u and little v. And you can define a big U and big V, or capital U and V coordinates, similar to our previous x and t in empty space with the similar formula. So we have the analog of space and time now, but in curved space-time, it turns out that this big U and this big V will not correspond to a fixed point in space and time, as we will see. So a particle which is freely floating or falling freely will not simply follow these curves u equals constant and v u equals constant, for example, but it will be more complicated. So here's what it looks like in practice. So this is the Schwarzschild black hole. So here we have a point mass at the center, and light rays are going in 45 degrees, as in previously. And we can follow the light rays forward and backwards along their world lines. And what we find is that they have an endpoint. So if you go along the light ray, it will reach a point where it can no longer go forward. And similarly, if you go backwards in time, it will reach a point where it can no longer, it doesn't have a past. So there's nowhere it can come from. So it's very interesting. In the case of black hole, there's this edge of space-time, singularity. And so here it is how it looks like in practice. So we can plot. So previously I was plotting these u and v coordinate systems, which were tracking the light rays, but we can also plot just the fixed spatial coordinate and fixed time coordinate. It makes sense to talk about fixed space and time coordinates in this case, because the black hole is at rest. So the black hole is at a fixed point in space. So relative to the black hole, you can say where you are. So space has a meaning, and you can measure, for example, the time along which you orbit a black hole, and that will define you a measure of length as well. So you can define it has meaning. Length, it's like fixed radius has a meaning in this case. So if you so here in this previous diagram, now I deleted the light rays, and I'm just showing you now the radial coordinates and the time coordinates. So clearly, space-time is now curved, so it's no longer a regular grid, but you can see that these curves represent constant radius curves. So for example, here the radius is equal to 100 kilometers. Here along this curve, the radius is equal to 80 kilometers, and so on. And there's a special curve which is straight actually in this case, which is the horizon. Here the radius is 30 kilometers. This is the case when you have a 10 solar mass black hole. And you can see that there's this curve where the radius is 0. So this is the origin of the coordinate system where the black hole is. And so you can also examine what happens to a particle. The particle is always moving in between the 45-degree light cone, because it cannot go faster than the speed of light. So it goes in the upward direction, and it will always necessarily hit this region, the singularity, if it goes in the inward direction. If it goes outside, if it travels outside, away from the black hole, increasing its radius, then it can escape. However, once you have reached this critical radius, which is, in this case, the Schwarzschild radius is 2 gm over c squared, but relativists usually use units where g is the gravitational constant and the speed of light are 1. In that case, you can write that r equals 2m. So once you're inside of this region, you can no longer escape back to infinity, because you can see that even if you go with the speed of light outwards, you still cannot exit this region. So your radial coordinate will still not increase. You would have to come, even faster than the speed of light to exit this region. So that's not possible. So this region inside here is called the black hole. So inside of the horizon, this region is called the black hole. And another thing that you can do is yet another coordinate system. You can introduce, instead of your previous, we had our u and v coordinates, which were tracking the light rays, the small u and small v coordinates. You can introduce this u prime and v prime coordinates with this arctangent function of our original u and v coordinates. And with this, you can map your original spacetime into a compact diagram shown here. So the advantage of this type of representation of spacetime is that it keeps our original description. So again, we still have light rays going along 45-degree lines inwards and outwards. But in this case, everything fits on a sheet of paper. So infinity is actually mapped to a region which is shown here on this diagram. For example, this is the future infinity, and this is the past infinity here. So, but otherwise, it's very similar to our previous image. So it's just that this region here is mapped into this region, and the black hole is mapped into this region. So it looks very similar, but you can now draw everything on a piece of paper. And so here, this line here is the singularity. So this corresponds to radius being equal to 0. And this region here, far from the black hole, behaves just as if it was an empty space. So here, the effects of the black hole is negligible. But what's interesting is that if you go into the black hole, there's this other region of space-time here. So it turns out that if you follow light rays backwards in time, you end up in this region, which is just like our universe. So it is asymptotically empty space, and it doesn't have curvature at infinity. It just looks as normal space. It cannot communicate with this part of space-time. These are sometimes called universe. This is one universe, and this is another asymptotically free universe. They cannot communicate only inside of the black hole. So it's interesting, if you fall into a black hole, you can be hit by a billiard ball, which is coming from the other side, other universe. So the black hole can, in fact, connect two universes. And here, you cannot have any information about the other universe, because you would need to travel with a speed larger than the speed of light to come here. But nevertheless, you can, if you jump into the horizon, you can find out whether or not this universe is feeding material into the black hole. And what's also interesting is that there's this region in the bottom here, which is called the white hole. So here, it turns out that, as you can see, that every object everything will exit, every particle will exit. So the particles are moving upwards within their light cones, so within these 45-degree lines. And so necessarily, everything will exit this region. So this is the inverse of a black hole. You cannot stay here. You will be thrown out by space-time from this region if you start out from here. So this is interesting, but so how would this look like from the outside? Well, it will look like something coming out of the black hole, basically, because we are looking in the direction of the black hole towards smaller radius, but it's not coming from the black hole because this is the black hole up here. So it's in fact a white hole in this case. So things can come out from here, but people believe that these white holes do not exist. It's just a hypothesis. It doesn't have any proof. In principle, you can have a white hole. This is the solution to Einstein's equation. So the point is that this diagram shown here is the most general solution to the static point. So static Einstein's equations around the point mass, which is at the center. Of course, this may or may not exist in nature, this type of solution. Just because it solves Einstein's equations, it's not necessary that it has been created and it exists. So, for example, if you think about how black holes form from collapsing dust, you will not form the white hole because the white hole is in the past. So once you have in the past, you don't have a black hole. So in the past, you just have a cloud of dust, which falls in radially. Then at some point, you will form a horizon, a trapped surface, and a singularity. So you will not have these parts of this diagram here. But you will only have these two parts of space-time. So it's a controversial question whether or not these regions of space-times exist, but it's interesting. You can, in principle, probe this observationally. So this was for a non-spinning black hole when you don't have any angular momentum. But if you have a rotating cloud of gas which collapses into a point, it will conserve its angular momentum, and the space-time will remember that the material forming it was rotating originally. In this case, you will have a spinning black hole. Sorry, so this was still for the non-spinning case. In the spinning case, you can draw the space-time this Penrose diagram, and it looks more complicated than the previous one. But so this is our universe on the lower right here. And we have a black hole. So again, there's a horizon. Light rays which are going inwards will go into the black hole. Light rays which are coming outwards can escape in this part of the universe. But once you reach the horizon, then light rays will not be able to exit. But what's interesting, again, you have this parallel universe which you can find out about if you cross the horizon, and you can have this white hole in the past here. But what's interesting here in this case is that the singularity itself has a shape of a ring. It's no longer a point. So you can actually fall into a spinning black hole, and if you're talented or you have a very good spaceship and the black hole is big enough, you can avoid the singularity, and in principle, if these parts of space-time exist, you can exit the black hole into another universe. So so in the other universe where you're exiting, it will look like as if you are coming from a white hole. So from looking from the other universe, it will look like as if material is coming out with some high velocity from this region. And so the question is whether or not, again, these types of spacetimes exist. If you just have a collapsing cloud of gas, you will not form the other universes. So you will not have anywhere to go to when you fall into the black holes. But who knows? We don't know in principle if the things that we see and we think are black holes are these types of black holes or the ones which formed in certain theoretical ways. So this is, I would say, still an open question, a fascinating question to think about. Okay, so here's a summary of the history, the early history of the black hole physics. So already in the 1800s, Jean Michel and Pierre Laplace discussed that you can have classical bodies where the escape velocity could be greater than the speed of light. In that case, the objects should be black. So this was already known in 1784 and 95. And so then Albert Einstein wrote down his field equations in 1915. And it's interesting that 5 days earlier, independently, David Hilbert also wrote down the same equations. They have communicated about this in the past. David Hilbert was a mathematician, and he derived Einstein's equations independently and in a very elegant way, actually. So I've already mentioned that Schwarzschild gave the solution to these equations in spherical symmetry in the static case around the point mass, which is the simplest thing that you can have. This is the Schwarzschild black hole solution. And then nothing much happened until 1958, when David Finkelstein suggested that the Schwarzschild radius is actually a barrier in causality, an event horizon. So this was so basically Finkelstein was one of the pioneers of these coordinate systems where they fixed the coordinates to the light rays and they understood what this singularity meant that came out from the equations. In 1963, Martin Schmidt discovered the first quasar, 3C273. So this was a very luminous source. And this was, we could call this the first discovery of a supermassive black hole. Of course, at the moment, they didn't know what it was. It was a radio observation, which later is known to be, the theory now is that it should be a supermassive black hole, as I will show you. In 63, Roy Kerr solved Einstein's vacuum equations for a rotating black hole. So this is the rotating black hole solution. This is another exact solution to relativity. In 64, the first stellar mass black hole was observed with a rocket by Riccardo Giacconi and Herb Gursky. And so they won the Nobel Prize in 2002. In 64, Roger Penrose proved that an imploding star will necessarily produce a singularity once it has formed an event horizon. So Roger Penrose is, of course, here at Oxford, and we're very proud that he won the Nobel Prize just last year for this discovery. In 64, Zeldovich and Salpeter proposed that gas disks, so-called accretion disks around supermassive black holes, are responsible for the huge amount of energy radiated by quasars. So they have already explained the discovery of Martin Schmidt with this in this way. So they hypothesized that it should be supermassive black holes which are responsible for this emission. and so on. I will not go through much of the detail of the history. Rather show you some specifics for evidence of black holes next. So active galactic nuclei are galaxies where what you can see that there's a very bright emission from the center of the galaxy. So this very small region, which is often less than 1 light year, outshines the whole galaxy. So it's brighter than all of the stars in the galaxy. And so this was observed in 1963 already. And what they have noticed is that this emission is variable. So it's not constant. And it varies over month timescales. So already from this fact that it varies on such short timescales means that the size of the emitting system cannot be larger than 1 light year or 1 light month. Because if you think about it, you would have a large galaxy. Let's say a galaxy is typically tens of thousands of light years, and it has billions of stars. If suddenly you see that the galaxy emission is a factor of 3 less than what it was before, that would require for all stars to coincidentally turn themselves off by a factor of 3 throughout the galaxy. And this is not possible because they cannot communicate faster than the speed of light. So it's very improbable for large systems to produce variable emission over timescales which is shorter than their effective light travel time distance across. So this already gave some indication that there's this huge source of emission concentrated in a very small region of space. The other observations showed that in fact there are these relativistic jets which are launched near black holes. You can measure the velocity of gas moving out from these regions, and you can find that this velocity is very, very close to the speed of light. It can be 0.999 times the speed of light, which is pretty impressive. And furthermore, you could observe that gas, which is orbiting around the center here, you can measure the spectrum of the gas, and you could see that the spectrum is relativistically broadened. So if you have particles moving around a point, then sometimes the particles go in your direction, sometimes moving away from your direction. So sometimes the emission that they produce will be blue shifted and sometimes red shifted. And so that means that an emission line would be broadened, and you can, just from measuring the width of a line, emission line, you can measure the velocity of the particles moving around. And in these regions, the velocity ends up being extremely large, bigger than 0.1 times the speed of light. So just from these observations, you can convince yourself that it cannot be anything else but something which is extremely dense, which can produce these types of effects. For example, if you have a star, material orbiting around the star cannot orbit with this velocity, because the orbital time around an object has to be less than the escape velocity from the surface. And from a star, the escape velocity is just 1,000 kilometers per second. It's not 0.1 times the speed of light. To have such large velocities, you have to have extremely dense objects. So these can be, we now know that they can be, for example, black holes. They can also be neutron stars, for example. Oops, sorry. And so these were active galactic nuclei. The other types of objects discovered in the same time, roughly speaking, were stellar mass black hole binaries. So what you see here is that you have a black hole which is orbiting a star. You cannot see the black hole typically, or sometimes you can't, sometimes you can. I mean, emission near the black hole, but you can typically see the star. So the star is orbiting around something, and you can, just from the Doppler shift of the motion of the star, you can infer the mass of the object around which it orbits. And for example, Cygnus X1 was shown to have mass bigger than 3 solar masses, just from the motion of the companion star. But the other thing is that the star can often inject material into the black hole, and once the black hole accretes this material can shine with extremely high luminosity. And so this is a source of highly variable X-ray emission, which you could observe already in 1964. And now we have many more examples of these systems. But the best evidence for black holes at the moment, with electromagnetic observations, is the supermassive black hole at the center of our own galaxy, the Milky Way. So in this region, you can see that there are stars orbiting around a point in space, and you can see in time that stars are orbiting on these trajectories. So one of these stars has this star S2, which is the closest star, has already made a complete revolution, almost 2 revolutions now around the center. So just by measuring very accurately the motion of these stars around the black holes, around this object, you can infer the mass that should be there in that region. And what you find is that within a few light days distance, you should have a mass which is 4.5 plus or minus 0.4 times 10 to the 6 solar masses. So an extremely large amount of mass is concentrated in this extremely small region. So you cannot see this, there's nothing in this region that you can see. There's only a radio source, a faint radio source. And this is why it is called Sagittarius A star. It's in the Sagittarius constellation on the sky. And so this discovery was awarded the Nobel Prize last year as well, in addition to Roger Penrose's Nobel Prize for the evidence of supermassive black holes. And so here's an inventory of electromagnetic observations of black holes and other compact objects. So what you can, just by observing the motion of stars around stellar mass black holes or neutron stars, you can measure the masses of these objects. And so this is one thing that you can measure. You don't know yet if it's actually a black hole or it's something else. All you know is that you can measure the mass and the size, roughly speaking, which is constrained by the orbit of the companion star. And what you find is that that the mass is clustered into 2 groups. There's one peak near 1.4 solar masses and one peak near 10 solar masses. So these objects are thought to be neutron stars, and these ones with 10 solar masses are believed to be black holes. So this was before gravitational waves were discovered. You already knew that there should be black holes based on electromagnetic emission. And there are also supermassive black holes. So these are much more massive. So here I'm showing the mass of the supermassive black holes for several different observations. So you can see that their masses are between 10 to the 6 solar masses and 10 to the 10 solar masses. And what's interesting is in galaxies, they're always at the center of the galaxies. and the size of their mass is correlated with the velocity of stars. But so you might think, well, of course it's correlated because stars are orbiting around the black holes, so they have to be connected. But this is not the case, because the region which is governed by the supermassive black hole in terms of its gravity is actually black hole mass is only large, which is much less than the mass of the whole galaxy. So that means that the mass of the supermassive black hole is actually negligible compared to the mass of the whole galaxy. So it's surprising that stars in the galactic bulge, which are not attracted by the black hole itself, are still, they still know about, in some way, what the mass of the supermassive black hole is, because they adjust their velocities in such a way that it's correlated. And so this was a surprise to, this is possible, because if you think about it, it turns out that the energy of the radiation emitted near a supermassive black hole can be proportional to the mass times c squared. mc squared is energy, which Einstein discovered. So the rest mass energy of a black hole, you can think of this as mc squared. And the radiation which is emitted from material falling into a black hole can be, by the time the black hole is built up to the given amount of mass that is being observed, is proportional to mc squared. So it can be, for example, 10% the energy which is emitted black hole. So that shows that the energy which is available, which is generated by the black hole, which can be, for example, absorbed by the galaxy which is far from the black hole, is quite high. It's mc squared of the mass of the supermassive black hole. And the energy of the kinetic energy of stars is mv squared, right? Where v is the velocity of the particles. The velocity of particles is only a few hundred kilometers per second, as you can see here, which is much less than the speed of light. So the speed of light is 300,000 kilometers per second. So it's 1,000 times larger. So the velocity of the particles is 1,000 times less. So even though the mass of the black hole is 100 times less, it can produce an energy which is bigger in comparison by the speed of light divided by the velocity to the second power. And since the velocity is 10 to the minus 3 times the speed of light, the black hole actually wins a factor of 10 to the 6. So the black hole can generate an energy which is 10 to the 6 times 0.2% times the energy of the particles. So that shows that there's plenty of energy available in the system. So the supermassive black hole can actually regulate star formation in the galaxy. And so there's the next subject is imaging black holes. So what does it look like? Can you make images of the black hole? So here's an image of a jet which is coming from the center of the galaxy. So there's a bright spot at the very center. This is near the black hole. And these are these relativistic particles which are flying out. And these jets can extend to hundreds of thousands of light years away from the black hole. And what's interesting is that the theory for gas accretion into the black hole is not very well understood. So it's not understood how actually gas can fall into the black hole, because the problem is, how do you get rid of angular momentum? Material falling into a point needs to get rid of its angular momentum to actually fall in. If you have some angular momentum to begin with, you will just orbit around the center, and you will not actually fall in. Only if you go straight into it to begin with, but that has a relatively low probability. So the big open question is how actually gas manages to go into the black holes, to grow the black holes. And similarly, the other big question is, why do we see these jets? So what is the mechanism which accelerates these particles to the 0.999 times the speed of light? So what is the mechanism which ejects the particles with such high velocity? And so there are theories about this. One of the theories has to do with Magneto Hydrodynamics, and Stephen Bulbous here at Oxford was one of the pioneers of this theory. But it's actually still not clear if this is, so this is the leading explanation for the possible explanation for the production of these jets, and accretion. But it's still actually not clear if this is the correct solution. So I would say it's still an open problem. And the other thing that would be nice if we could image the black holes is to just test general relativity itself in the very strong field regime, test whether what we see at the center is actually a black hole or something else. Is general relativity the correct theory of gravity or not? It needs to be tested. And the other interesting question is whether there are quantum effects near the horizon of the black hole. There's this whole subject of firewalls. You can, in quantum mechanics, you can form pairs in vacuum with a particle and an antiparticle, which can annihilate to nothing. So in vacuum, you can form particles and disappear particles. But near the horizon, you could have one particle which could fall into the black hole, and one could come out. And if these particles are quantum mechanically entangled to begin with, you can have a problem, an information paradox near the horizons of these black holes. So there are plenty of questions to think about. And of course, the big question is if near the, so how does general relativity break down near the singularity? So the goal is to image the black holes in some way or another. So one thing that you can do is to do numerical simulations. So how does gas orbiting around the black hole look like? And what type of electromagnetic signatures you could look for if there's gas orbiting around the black hole? So this is a simulation of a hotspot of a hot gas cloud orbiting around the black hole. And you can typically, you don't have the resolution to see the gas going around a dark spot, but you can calculate it on a computer. And then you can simulate what it would look like if you look at this with a low resolution instrument. So one thing that you can look at is just the time variation of the luminosity as a function of time. You see that as the gas cloud is coming at your direction along the line of sight, it will be Doppler beamed, so it will be much brighter than when it is receding from you from along the line of sight. But this depends on the inclination of the orbit. You should see this time variation, which looks like what's shown here. So let me show you again. So again, this is if you're looking at these hotspots from above. But if you're looking at it from some angle, from some inclination, then it appears to be curved. And this disk, which is a flat disk, appears to be significantly warped by the curvature of the black hole itself. So this is one thing that you can look for. And the other, so you can do numerical simulations. And this is another open field which is quickly developing at present. These are simulations which have these acronyms. GRMHD is short for General Relativistic Magneto Hydrodynamic Simulations. And what's interesting here is what is missing from this simulation. What is the reason why it's not realistic, why you shouldn't take it for granted, is, for example, because in these types of simulation, typically or often, radiation effects are neglected. Radiation pressure itself is neglected. But general relativistic effects are included, and magneto hydrodynamics effects are included. So it's still in progress. This research is in progress, but it's not fully developed yet. More recently, there are now simulations which also include radiation effects, but they may not have still the resolution to actually solve the problem of accretion itself completely. So this is how it looks like, and you can see that there are these. You can see that there's radiation appearing to come from the black hole itself, but this is just an illusion, because again, there are particles there are light rays which are orbiting around the black hole, and they appear to be coming from the direction of the black hole, whereas in reality, this is what it looks like. But this cloud looks like this gas disk. Okay, so the black hole shadow is something that you can look for, and this is what you can look for. So here, what is shown at the center is a black hole, and there are light rays. So you can solve again Einstein's equations and just plot how the light rays propagate around the black hole in this coordinate system. And so what you should see is the light rays which are escaping to infinity. But since you have a black hole here in the foreground, it will absorb light rays coming from just behind this region. So there will be a shadow cast by the black hole. And you can measure the shape of the shadow cast by the black hole, and then test general relativity in this way. So you can so black holes have spin parameters which describe how big of an angular momentum they have. And they are typically these Kerr type black holes. The spin parameter can be between -1 and 1. 1 being the extreme case when the horizon is basically orbiting with the speed of light, and that's the maximum that they can rotate with. And so it shows that if the black hole is spinning, then the image of the shadow will be distorted for highly spinning black holes. So if you measure very accurately the shape of the shadow, you can test whether or not this is actually consistent with general relativity. And so you can think about how to make an image of a black hole, what type of instrument you will need. And it turns out that you need the size of the instrument should be the size of the Earth, because typically you can observe in millimeter emission, because usually these regions are very very difficult to observe in other wavelengths. They are obscured by dust. But in these types of millimeter and submillimeter wavelength, you can the light rays can basically escape or cross the medium, and you can observe this material in these wavelengths. And you can calculate what is the diffraction limit of this instrument if you have such a large instrument. So first of all, you know what the size of a black hole is, because you know the mass of the, for example, supermassive black hole at the center of the Milky Way. It's 4 million solar masses, and you know the distance. So you know the angular size of the black hole on the sky. So you can think about how big of an instrument you need to resolve this object. And just from the diffraction limiting formula, it turns out that the size of this object is 11 micro arcseconds, and the size of the dish turns out it should be comparable to the size of Earth. So if you think about it, you may be worried that it's not possible to make a telescope the size of the Earth, but in fact, it is not impossible. What you need to do is basically put telescopes or receivers, radio antennas, on various points around the Earth and measure the signal very accurately, phase coherently, and then correlate the signal of the different instruments with one another. And thereby you get an instrument which has the effective size of the Earth. So this is how you can image a black hole. So Sagittarius A star is the largest black hole on the sky. It's 10 micro arcseconds. And the other object that you can measure is M87. So this is an active galaxy, which is not very far. Here the black hole is much more massive than in our own galaxy. It's 1,000 times more massive, but it's 1,400 times more massive, but it's 2,000 times farther away than Sagittarius A star. So this suggests that that the angular size of this object is within a factor of 2. It's the same, because the size, the Schwarzschild radius, is just proportional to the mass, but the distance, the size is also the angular size is inversely proportional to the distance. So these two factors just cancel out. So M87, the angular size of M87 on the sky is roughly the same as that of Sagittarius A star, the supermassive black hole at the center of the Milky Way. But the advantage of this much bigger black hole is that it fluctuates in time much less rapidly. So there's material, and furthermore, there's material which is going into the black hole. So it generates a bright emission, and even though it's far away, it can still be observed. And it's not as variable, so you can integrate with instruments for much longer than for Sagittarius A star, and try to dig out the signal from the noise. So there's some advantage to observing larger objects compared to smaller objects. And you can correlate, again, these different instruments at sub-millimeter wavelengths. And you can calculate what should be, what type of image you can hope to see with this instrument, so-called Event Horizon Telescope. This is the simulated image if you would have an infinite resolution. But since you have just a finite number of these instruments around the Earth, and you have the diffraction limit, this is how it should look like. And so this is the Event Horizon Telescope. And very well in 2019. This was the image that was produced by the Event Horizon Telescope. So it's very nice. You can see the shadow of the black hole clearly. You can see a rim, which may be due to the strong Doppler shift of the material which is orbiting around the black hole. So this is indication that, in fact, these objects are black holes and not something else. So the theory of general relativity stood the test, at least for now. Okay, so let me just show you another example. So of observing black holes. This is using microlensing. So in the case of microlensing, what you're looking for is you're trying to image a distant black hole, such as a quasar, and you're using the fact that there's a star in the foreground, which is lensing by gravitational lensing, it lensing the light of the quasar. And as the object goes in front of the line of sight along where the quasar is, it bends the light rays coming from the quasar, so it produces a time variability which you can calculate. So as it goes in front of along the line of sight, it focuses by gravitational focusing, it focuses the light to you. So that means that the light will be more luminous than previously. And then as it goes away, it becomes the original luminosity. So just from this time variability, you can measure the size of the emitting region. You can resolve the point source, which would be otherwise not resolved without this technique. So with this technique, you can hope to resolve objects which are much farther than M87. And this is what you find. So here I'm showing, I'm comparing the size of the emitting region as a function of the mass of the black hole. And the theory predicts, so if Magneto Hydrodynamic, so MHD is responsible for accretion, you can calculate using the simulations I've shown you before what should be the flux coming from different parts of the accretion disk. You can simulate what should be the size of the emitting region if the object is going in front of the line of sight. And what you find is this thick red line. And what's interesting is that the size of the emitting region found from microlensing happens to be an order of magnitude larger. So this is something which is not well understood at the moment. It's a puzzle. So why is it that it seems like that these sources are much larger than predicted by general relativity? So this is an interesting observation that I wanted to show you. It shows that this field is still an open, exciting subject to study. And so let me show you some the search for black hole binaries in the universe. So what you can see, as if you look at the sky, is that many galaxies merge along their history in the universe. So if you look up on the sky, the percent of the galaxies or so, maybe 0.1%, seem to be merging galaxies. You can see these tidal streams which are produced during the mergers of galaxies, and you have distinct cores of these galaxies observed in this picture. So these appear to be irregular type galaxies. So there are plenty of observations of these binary merging galaxies, and in many cases they are not only merging galaxies, but they have an active galactic nucleus. So there's a supermassive black hole at the center, which is at the moment eating gas and shines very brightly. So this is an AGN. And in fact, you have these binary AGNs. So both of them during the merger are accreting gas. And you can see that some of the examples of these images when you have two AGNs very close together. So the separation here between the black holes is of order kiloparsecs. The big question is whether or not these black holes merge with one another often in the universe, how they have grown to become so large as we see today. How did the supermassive black holes form and grow in the universe? So we're searching for very short separation supermassive black holes. This is one of the interesting fields in astronomy. And let me show you some examples. So here's an optical image of a galaxy, and at the center, if you look in X-rays, you can see two bright spots, which are actually here zoomed in different X-ray frequencies. You see that these are two distinct black holes emitting at the center of this irregular galaxy. And here's another example. So here's another galaxy where you can measure the well, you see two bright spots at the center. And so the record at the moment for these supermassive black holes is this one. Then you see from radio observations that you have two bright spots, which are separated in this case by 7 parsecs. And here the total mass is something like 10 to the 9 solar masses. So you have 2 billion solar mass black holes with a separation of only 7 parsecs. The parsec is the order of magnitude is a light year, few light years. So it's just something like 10 or 20 light years separation. You find 2 billion solar mass black holes. But we are looking for even smaller separation black holes. We are looking for subparsec binaries. So here's a Nature paper in 2017 which claimed that there's a subparsec binary with projected separation of 0.35 parsecs. So this is another exciting candidate. And finally, there was this other Nature paper in 2015, which has shown signs of two supermassive black holes at a separation of 0.01 parsecs now. So in this case, you didn't have the resolution to actually distinctly identify two supermassive black holes in an image, but what was seen is a time variability which showed an orbit which showed evidence for variability on timescales of something like 10 years or 5.2 years. And this type of variability occurred in all different wavelengths. And in fact, you can calculate if you have two supermassive black holes in orbit, let's say a 5-year orbit, then during the orbit, once the black hole is going in your direction, again, it's Doppler beaming the light towards you, and once it's going away, it's Doppler beaming away from you. So there should be a variation because of Doppler beaming that you can calculate, and it will be different in different wavelengths. So the amplitude of this variation will be different, and you can measure the amplitude, and it just matched the observations. So it was quite exciting that it is matching the theory. So if it's Doppler shift which is causing this type of variation, then this is what you should see. If you would have two black holes with 10 to the 8.5 solar masses orbiting at 0.01 parsec around one another. So this is one of the candidates for merging supermassive black holes. And finally, what you can see is gravitational waves from two merging black holes. So when they actually merge, they produce gravitational waves. And so this is another interesting subject in physics, numerical relativity, which is people have been trying to solve Einstein's equations on a computer when two black holes are close to one another. It turns out that this endeavor is very, very complicated. So in the simulations have encountered infinities. So you naturally do approximations in the simulations when you do numerical simulations, and these approximations turned out to grow with time always in the simulation and became unstable. So meaning that small perturbations have grown to infinitely large perturbations, and so then the solution was not possible for a long time. So there was a breakthrough in 2005 when Franz Pretorius tried a new technique to do the numerical simulation, and he managed to merge two black holes in a computer simulation. And independently, within a year, there were three other groups which could merge black holes. So now this is a solved problem. So there are many different numerical techniques which can be used to merge the black holes, and they all produce the same result. So we actually know now very accurately what the signal should look like if you merge two black holes together. So let me show you. So here are two black holes, and I'm plotting the gravitational field lines. And as the black holes are coming closer to one another, they are emitting this stronger and stronger gravitational radiation. So the gravitational field lines are propagating with the speed of light, and in the end, they form a merged remnant black hole, which is a spinning black hole typically. So this is something that you can now solve on a computer, and you can try to look for these types of gravitational waves. So the gravitational waves are similar to electromagnetic waves in that they propagate with the speed of light, but they basically produce a space-time distortion. So if you have two objects going around one another, they generate these gravitational waves, which, if they interact with matter, they produce these oscillations in matter, and they produce relative distortions. So bigger objects will be distorted by a bigger amount in proportional to its size. And the effect, the amplitude of the distortion scales with 1 over the radius, and you have two polarizations. So these are gravitational waves. And you can hope to detect gravitational waves with different techniques. So there's LIGO and also Virgo, the European and the American and the European Gravitational Wave Observatory, which uses these 3 or 4 kilometer long cavities where you have a laser beam which is split into two to travel along these cavities, and there's a mirror at the end of the cavity, and the light rays bounce back and they produce interferometry. So they basically measure the length of the cavity of the arm of the detector very, very, very accurately. And if there's a gravitational wave which passes through the system, the length of the arm will vary in proportional to the amplitude of the gravitational wave. And it produces a small interference at the once it comes back to the to this point in the instrument. And so you can use this technique to detect gravitational waves which are comparable to the size of the system. The wavelength should be comparable, or maybe 100 times larger than the size of the system. which is typically these types of gravitational waves with wavelengths of a few hundred kilometers are emitted by stellar mass black holes. And they cannot detect supermassive black holes because those waves are too long wavelength. You also have, in the future, maybe you will have LISA. This is a planned instrument. You have 3 satellites which are flying in space, trailing Earth around the sun, and they do interferometry between them. But here, the separation between the satellites can be much larger. So it can be millions of kilometers, 5 million kilometers, something like that. And so it will be sensitive to waves which are coming from supermassive black holes here. Another technique is to use pulsars. So pulsars are spinning neutron stars, which are sending these beams of radio pulses very, very accurately in succession to us. So we can use these pulsars as the instruments. So we are detecting pulses from pulsars in different directions around the Earth, and we are using them as the instruments. So as the gravitational waves pass through the pulsar Earth system, the arrival times of these pulses will be delayed by the gravitational waves, so that you can detect gravitational waves in that way. So here the distance is much, much larger. So you can detect the largest supermassive black holes and the ones which are not even merging, but only orbiting around one another with periods of years to tens of years. So these are the 3 techniques to detect gravitational waves from merging black hole binaries. So here's an example. So here's the plot of the frequency band of gravitational waves detected by different types of instruments. And here's the characteristic strain, so the amplitude of the gravitational wave, and the plot shows the sensitivity of the instruments, or the planned sensitivity of the instruments in many cases. So on the right here, you see at 100 hertz or up to 1000 hertz, there's LIGO and Virgo. There are these Earth-based gravitational wave instruments. And also I should say Kagra, the Japanese instrument, is also now available. And maybe in the future, there will be future versions of this where the sensitivity will go down. And so you have sources shown here with these shaded regions, which if they happen to be above the sensitivity of the curve, the limiting sensitivity, and they will be detected. So this is already possible now, but in the future, maybe in a few years, you will be able to detect these supermassive black holes orbiting around one another with these pulsar timing, and the merging supermassive black holes with LISA, the space-based instrument. So this is a very exciting field of research at the moment. You can make predictions for what type of sources you expect, and you can hope to find in the near future. And so, as I've said, LIGO has already detected gravitational waves several times. So here are some examples. So these are showing for different merging systems the signal which has arrived in the instrument. So it has shown that the frequency of the signal has been increasing. So the wavelength was decreasing and the amplitude was increasing, just as predicted by the numerical relativity simulations. So comparing the simulations to the observed signals, you can measure the masses of the merged objects, and you can test the theory of relativity. So here's the present landscape. So here are the observed LIGO Virgo black hole sources. So you can see that you have what is plotted is the masses. So you have, for example, here two a 20 and a 30 solar mass object merging, and it produces a merger remnant of around 40 solar masses. And in some cases, you produce a merger remnant. So one case, you had a black hole mass of 50 solar masses and a 90 solar mass object which produced a 160 solar mass black hole. And this is not even everything, because it's only in the first 3 observing runs of the instruments. So this is up to early last year, or maybe 2 years ago. The newest data are not included. So there was one source in which 2 100 solar mass black holes merged, and they produced a 200 solar mass black hole. Maybe 120 or 130 solar mass black hole merged with another one. So it produced a black hole which was over 200 solar masses. You also have electromagnetic observations of black holes, which I've shown you before, which seem to have clustered around 10 solar masses. So it's surprising a bit that the electromagnetic observations show objects which are lower mass than the gravitational wave observations. We think we understand why that is, but it is still an open field of research. So one possibility is that LIGO is just more sensitive to the more massive black holes. And this is why LIGO has seen these objects, and electromagnetic observations cannot see these types of sources because they are relatively rare. And there are all these electromagnetic observations of neutron stars. And there was 2 events when 2 neutron stars merged and produced something which was not seen in gravitational waves, but presumably they were a black hole. So this is a very, very exciting new field of research. It's a completely new sky on the universe, which will probably hold many surprises. So every time a new type of observation became possible, new types of detections, new discoveries have been made. So for example, when radio observations were made of the universe, it was realized that some of the galaxies have these very bright radio emission from their centers. So basically discovering supermassive black holes. Similarly, X-ray observations have shown evidence for neutron stars, and microwave observations have shown evidence for the Big Bang itself with the cosmic microwave background and so on. So every time you open a new field of observations, a new wavelength of observations, you find something completely new. So it will be really exciting to see something new. So we already know that black holes exist and we see them in gravitational waves, but as the instruments will become more and more sensitive, maybe we will find something which is completely unexpected. So this is a very exciting field of research, which is now finally possible. Let me just go on with explaining what you can detect with gravitational wave observations. So one thing which I discussed earlier is the mass, and the other possibility that you can measure are the spins. So black holes which have angular momentum have spins. They are these Kerr type black holes, and I told you before that the spin parameter can be between -1 and 1. 1 meaning that it has a maximum spin and in one direction, and -1 would correspond to maximum spin in the opposite direction. And you can measure the spin of these black hole mergers, and it turns out that the spin, the effective spin parameter, which is this combination of the spins, basically weighted by their masses and spin directions. It's a projection of the spin actually. This parameter also should be between -1 and 1. This parameter has to actually is found to cluster around 0. So somehow these black holes are either not spinning very rapidly, which are observed by LIGO and Virgo, or they are spinning in such a way that the spin vector direction is perpendicular to the orbital plane. It turns out that what we are sensitive to is the component which is the component, the spin vector, which is along the orbital angular momentum of the system, so which is perpendicular to the orbital plane. This is the component that we are sensitive to. So, but if the black hole spin is along the orbital plane, in that case, this projected spin parameter will be 0. So either for some reason the spins of the black holes align in that direction, or they are intrinsically small. So this is another open question. So why is this? Maybe it tells us something about the formation channel, about how the black holes actually come together and merge astrophysically. So what we have learned so far is that black holes exist. So these simulations show that numerical relativity matches. So general relativity is actually very well matched to the observations. So you can predict how the black holes, as they come together, orbit around one another and in spiral slowly, and then they merge, so their horizons coalesce, and then the merger remnant settles down to a stationary Kerr black hole in this ring down phase of gravitational waves. And so the theory matches the observations at the moment. And so you can test the theory of gravity. So there are alternatives to the theory of gravity. For example, in this case, so in the theory of gravity, the mass of the gravitational waves, the quantum mechanical particle, which corresponds to the gravitational wave, is which is called the graviton, has 0 mass. So if something has 0 mass, it can propagate with the speed of light, 0 rest mass, I should say. So the photons have also 0 rest mass, so they can propagate with the speed of light. So you can test whether or not the waves were propagating with the speed of light, and you find that the mass of the graviton is constrained to within 10 to the minus 22 electron volts, the rest mass energy, which is extremely small, so that you can calculate the Compton wavelength for this one. It turns out to be bigger than 1 light year. So it's a good approximation. This is consistent with the general relativity. And what was surprising is that stellar mass black holes may be more massive than previously thought. So 30 solar masses are actually common among gravitational wave sources. And the highest mass sources, as I said, was larger than 100 solar mass. So these types of objects exist. And not only do they exist in isolation, but they actually manage to merge with one another. So they find each other in space, and they merge relatively frequently. So previous estimates for the mergers of black holes were not as optimistic as the observed rate of mergers. So somehow there's this very large population of merging black hole sources, which are not clear where they are coming from. And there was also one big surprise that during one merger, black hole merger, there was also an electromagnetic gamma ray burst coincident with the merger. Actually, it was the first source. So it was a very big coincidence, because these gamma ray bursts are observed roughly 1 per day. What is the probability to observe something in the same second as the gravitational wave event which happened? But it's controversial. People think that this may just be a chance coincidence. But it's still an interesting open question whether or not you expect to see any type of electromagnetic radiation during a merger of 2 black holes. So here's a plot of the merger rates. So just from the first 2 detections, you could constrain the merger rate to be between the merger rate density in the universe to be between 2 and 600 per gigaparsec cube per year. And as newer and newer detections came along, these estimates became better and better. And so now we have something like 50 black hole detections. And the current estimate is shown here. It's around 20 per gigaparsec cube per year. It's relatively high, higher than previously thought. And the rate of neutron star coalescence is even higher. It's between 80 and 810 per gigaparsec cube per year. So now you can start making distance from the Earth, and you can see that you can start to compare the observations with theory. There are several big questions. How did the black holes form? The collapse of the first stars may be a possibility. You could have runaway collisions in dense star clusters. So these are how do the supermassive black holes form actually? Another question is how the stellar mass black holes form. And they are believed to form from stellar collapse. But in that case, because the progenitor stars need to be extremely massive and avoid some complications, their instability, supernova, and so on. So it's not completely clear at the moment how these black holes form. It's also not clear how they grow, how they actually accrete gas, how do they collide, why do they collide so often, or are they eating stars? So how often do black holes merge with stars, for example, to grow? Do they influence their environment? So these black hole mergers, these black holes, even if they are isolated at the centers of galaxies, you have these supermassive black holes. How do they actually communicate with the other regions of the galaxy such that they produce this correlation which I was showing you? One idea is that they somehow quench star formation in the galaxy, but there are other possibilities. Another open question is how do they launch jets, which go with almost the speed of light? It's not. Why do they merge and where do they merge? And are they really black holes? So these are the big questions. And let me just show you some of the interesting ideas for some of these questions. But as I said, it's an open field. So here's how two black hole binaries may form. This is one of the possible theories. I should say all the theories have their own shortcomings. So this one has two stars to begin with. These are common. So stars are commonly in binaries in the universe, especially massive stars, which will form black holes. Low mass stars will form white dwarfs or neutron stars. They are less, in proportion, less commonly in binaries, but these very massive stars are very often in binaries. And sometimes they are in close binaries, such that when one of the stars becomes a red giant, it will feed the other star with its own material, and eventually it will turn into a black hole. And if it manages to remain in the system, so if it's not ejected with some birth kick that can be received during a supernova explosion, then it remains in the binary. And actually first it just gets rid of its helium envelope. First it produces a Wolf-Rayet star, but then it's fed by the other object, which becomes a red giant, and in fact it can completely engulf the other object. So you can have one object so you can have a compact object and orbiting inside of a star. And eventually this star can also explode and become a black hole. And so you will have two black holes orbiting around one another. And eventually, due to gravitational wave emission, they can merge. But the problem is that they need to be extremely close to begin with. They need to have the separation here of order, the size or the distance between Mercury and the Sun. So less than 0.1 astronomical units. That needs to be the separation so that gravitational waves can merge the black holes within a Hubble time. So if the black holes are initially farther apart, they will never merge within a Hubble time. So somehow these black holes end up in such small separation. It is not very well understood how that happens. And also this line of argument implies that the black holes will be typically highly spinning. At least one of them will be highly spinning, because accretion, if it accretes gas from the companion, spins up the black hole. So the prediction is that these black holes will be highly spinning, and the spin configuration will be in an aligned configuration. But the observations show that this is not the case. The spin is either low or in the perpendicular direction. So this is one possible idea, and there are these shortcomings, and there are ideas how to circumvent these shortcomings, but I don't have time to explain this. It's a very exciting subject. And finally, you can make predictions for what will be the mass of the black hole from stellar evolution. Turns out it depends on what is the metallicity of the star. What is the composition of the progenitor star? The star, like the Sun, which has so-called solar metallicity, so it has elements beyond helium in abundance characteristic of the Sun. These types of stars will create typically neutron stars depending on their mass, but if they're massive enough, they can create black holes. Or if they're even more massive, they can create neutron stars. The problem is if you have high metallicity like the Sun, then most of the mass will be ejected from the Sun due to radiation pressure. So the solar wind gets rid of most of the mass, even if the star is very massive. So the remnant will not be massive enough. But if the metallicity is much lower, which happens to be in some cases, it's rare, but it happens, then you can avoid a lot of these ejections, and most of the mass will collapse into the black hole. So then you can form a black hole by fallback, or you can form by direct collapse. So in principle, you can form them, and there are theories explaining the formation of black holes. The difficulty is to explain the actual masses of the most massive black holes. So, and a question is, can you feed the black holes with gas? So if you have, suppose you put the black holes in a medium of gas, how quickly will they grow? And can you just grow them from an initially small size to, for example, a supermassive black hole? It's an interesting question. And there are different ideas for growing black holes through feeding accretion, shown here. And I will not go through all of this, just highlight Bundy accretion and disk accretion. I will not talk about circumbinary disks, so you can have two black holes in a gas environment, which is interesting. And you can also have stars flying around the black hole, which are torn apart and falling into the black hole. And you can have accretion from companion stars. So let me just show you, for an example, what Bondi accretion looks like. So this is the simplest estimate that you can make. So you can come up with this if you're a clever high school student. You can actually derive what is the rate at which gas can flow into an object. So it's a Newtonian calculation, so a non-relativistic calculation, but it turns out non-relativistic calculations are often sufficient, even though the black holes are completely relativistic. They are relatively produce a surprisingly good approximation of the true result, which you can do with a fully relativistic calculation. But just with a non-relativistic calculation, what you can examine is, suppose you put in a black hole in this wind chamber or something like this case, when you have gas flying with some initial velocity denoted by v infinity, and ask what will be the region from this flow which will be captured by the black hole. So of course, it should be the case where this v infinity is less than the escape speed from the black hole, right? So the energy per unit mass should be negative, and then the black hole has a chance to capture the gas. So you can just write down this equation for the energy. It's kinetic energy plus potential energy, the Newtonian potential energy. And so you can calculate what is the radius at which it will be captured by solving this equation. And this is called the Bondi radius. And so once you know this radius, you can just substitute in this equation. So ask what is the rate at which mass is flowing into the black hole. It's just rho, the density of the gas, times the volume per unit mass. The volume is just the area times the distance traversed by the gas over time dt. And the area is just pi times r squared here. And dx over dt is just the velocity, it's v infinity. So you can see that the inflow rate should be proportional to density of gas times pi r squared, where r is this the capture radius, the so-called Bondi radius, squared times v infinity. And if you substitute here rb, then you get this expression. And okay, so this will give you the rate at which the mass of the black hole grows with time. And what's interesting is, well, the other thing that you can investigate is what if the cloud has also some temperature. So here the assumption was that it was just a laminar flow. But if there's thermal velocity, then you have to modify the result a bit. It turns out that you have to replace v infinity squared with the v infinity squared plus the thermal motion squared of the particles, which is basically the speed of sound squared in the medium. So this depends on the temperature. So basically, if you make this change in the formula, then you will get the correct growth rate, the secretion rate. So this is a differential equation. It depends on the mass and time. So you can try to solve this differential equation. And I don't want to go through the details. It's a very simple separable differential equation. But what's interesting is that you find that it's a super exponential growth. So if the derivative was proportional to mass to the first power, it would be exponential growth. But now, as you could see here, it's proportional to the second power of mass, meaning that the growth rate of the black hole is larger, is faster than the exponential growth rate. In fact, it's a hyperbolic growth, meaning that in a finite time, you reach an infinite mass. So clearly something has gone wrong in the calculation. And of course, you can go back and check what you did wrong. It turns out that we neglected the infall time from the Bondi radius. We just assumed that everything is instantaneously gobbled up by the black hole once it reached the boundary radius. We assume that there's an infinite mass supply, which in reality is of course not the case. And importantly, we neglected angular momentum and we neglected radiation pressure. So you can try to fix these assumptions, and there are other difficulties. I don't have time to go into them, but you can have in principle turbulence, for example, which changes everything. You have to include relativity and so on, and radiation effects. So there are simulations. It's an active field of research. But let me show you the simple case of radiation feedback. So again, the question is, how do black holes grow? So now we assume that the material which is falling in has some pressure. If it is growing with the maximum rate, then the pressure that it's producing by radiation just counteracts, just halts the accretion. So at the maximum accretion, the accretion will be halted by radiation pressure. So we can just write down the Euler equation in hydrostatic equilibrium, and where the pressure here is due to radiation pressure. I don't want to go through all the details, but you can show that if it's radiation pressure, then it's opacity over C times the radiation flux. So this will be delta P over rho. So opacity is just the fraction of radiation energy, which is actually absorbed by the medium, but it's just a constant. For example, it can be the Thomson cross section divided by the proton mass. So it's just a constant. So in the end, what we have is that in this equation, that the gradient of the potential is proportional to the flux. And what we want to find out is what is the maximum luminosity, which is emitted by the black hole. The luminosity is the rate of energy released by the black hole. It is basically the surface area times the flux. So we have to integrate the flux over the source, over a closed surface. And so we can just substitute from this formula. The flux was proportional to the gradient of the potential, which we can substitute. And this will be the luminosity. So now we can do some tricks, algebraic tricks, to find out what this is, to simplify this. So you can use Gauss's theorem and show that if you have an integral of a gradient across a surface, it is actually the volume integral of the divergence of this gradient, which is the Laplacian of the potential. And the Laplace of the potential is known from Poisson's equation. It's proportional to the density. And if you substitute, you find you have to integrate the density over the volume, which is the mass. So you get a formula that the luminosity, the maximum luminosity, will be proportional to the mass. And so this is the maximum luminosity that a black hole can emit. And you can calculate in physical units. It turns out it's 3 times 10 to the 4 times the mass divided by the mass of sun times the luminosity of the sun. But the typical black hole, as I was showing you, is between 1 million to 1 billion solar masses. Suppose, for example, you have 1 million solar masses, that's the minimum for a supermassive black hole, then you have 10 to the 10 times the luminosity of the sun. And you know, a galaxy has something like 10 to the 10 stars, or 10 to the 11 stars, it's comparable. And if you have 1 billion solar mass black holes, it will be much brighter than the luminosity of all stars in the galaxy. So that's interesting. So this is just the luminosity, and you can go and calculate the growth rate. So if you have some luminosity corresponding to some fraction of the rest mass energy of the gas which is falling in, typically, you can solve this for material falling into a black hole. You can find that the fraction of rest mass energy of the gas, which is released in radiation, should be something like 10% for a non-spinning black hole. It's something like 42% for a maximally spinning black hole. And so this is this epsilon parameter. So you can ask, okay, if the fraction of material is ejected, but the rest will be accreted by the black hole. It will be 1 minus epsilon times the gas, the original gas mass. And if you solve this equation m dot for the luminosity, and you substitute the Eddington luminosity derived in the previous slide, then you find that the growth rate is now proportional to this factor. And what's interesting here is just now linearly proportional to the mass. So this shows that now it's an exponential growth. It's not this crazy super exponential growth. So then our differential equation for the growth of the black hole mass will be mass of the black hole divided by this time, which you can calculate. If it shines with the Eddington luminosity, this will be order unity here. Epsilon is of order 0.1 to 0.4. This will be of order unity. So in the end, you find that the black hole doubles its mass or increases its mass by a factor of E in a time which is 4 times 10 to the 7 years. So it's 40 million years. It's less than the age of the universe, but not much less. It's 1,000 times less, let's say, meaning that it could have increased its mass by 1,000 E-folds. But the problem is that there are very massive, supermassive black holes seen at very early times in the universe. So 10 to the 10 solar mass black holes are observed when the universe is only 10 to the 9 years old. So in that case, you only had something like 10 or 20 Eddington timescales. So you could only grow your mass with a factor of e to the 10. And if you start from a solar mass, you will not reach this mass. So to reach a supermassive black hole mass in such a short amount of time, this is not fast enough, this type of growth. So there's a problem with forming supermassive black holes. This is I wanted to highlight. I think I'm running out of time, so let me just jump to the conclusions. I could have also talked to you about the astrophysical origin of the mergers. It's not black holes so often, so frequently. And there are different ideas. One is just binary evolution. The other is dense star clusters. And the third is that the dark matter in the universe is made up of black holes, and that is responsible for forming all these mergers. There's also questions about intermediate mass black holes. But to summarize, black holes are finally observed in the universe. Surely they exist. There are supermassive black holes found at the centers of the galaxies. They are engines of extremely bright emission. The shadows of the black holes may be resolved now. There are gravitational waves, which have opened a new window on the universe. And there are lots of questions and research opportunities. So I would encourage all of you to think about this as a possible direction of research. And there's a bright future in this field. Thank you very much.
Thank you so much. Yeah, it was one of our longer talks. So I know a couple of people had to leave at some point. That's understandable. Thank you for everyone who's still here. We have a couple of questions in the chat. If you have any questions, put them in the chat, and I'll call them out. And then you can unmute yourself and ask them yourself if you would like to. I think Maria had to leave, so I'm going to skip her question. And then William had a question about white holes. So you were talking about how they couldn't form by collapsing matter. So he's asking if you think we can still find white holes, even.
Yeah, so it is not. So what is seen is that we see these objects which seem to be black holes, and there are very often these relativistic jets which are emerging from these black holes. So one crazy idea is that what is coming out is just material from some other universe. So in principle, it cannot be excluded that the material which we see very commonly coming out at these relativistic speeds is the material which just crossed the black hole. But of course, this is not the common explanation. So you want to explain these observations without invoking another universe usually. So the idea is that the black holes were formed by the collapse of stars, for example, and there's gas which is approaching the black hole, which is somehow due to some electromagnetic mechanism accelerated, and this is responsible for forming these jets. But who knows? So in the future, maybe you can this will be tested by observations, and you can maybe rule out or confirm that there are white holes in the universe.
Yeah, it definitely seems like something where we are gonna see a lot of new experiments soon with new results. It's gonna be a really interesting space to watch. So it's great to get this talk for people to kind of get a background and an understanding of the field as it is. Does anyone else have any questions?
So I wanted to say thank you. It was very interesting and definitely a lot of different topics to cover when talking about all this stuff about black holes. I know you mentioned curved black holes, the rotating ones at some point. Could we view those as just like transform ourselves into a rotating reference frame and then they'd behave like other ones, or is there some reason that wouldn't work? I know you mentioned that we had to be studying stationary black holes at the beginning.
There's a problem with sitting into a rotating reference frame in relativity. If you think about it, your reference frame, the velocity of the frame will be the angular velocity times the radius, right? In a rotating frame. So if you're far away, this velocity will be larger than the speed of light, right? So rotating reference frame will be rotating at speeds which is larger than the speed of light in the outside region. So it's not straightforward in relativity to switch to a rotating frame. And so it was quite a challenge to actually solve Einstein's equations in the case of rotation. It was not simply rotating the solution, the Schwarzschild solution, for example. It is one of these brilliant derivations produced by Roy Kerr.
Cool. Great. I don't think we've got any more questions in the chat. As always, if you do end up having questions and you may be interested in working with people or one of our speakers, do send them an email. People who come here to speak with us, speak for you, they're interested in, talking about their work, and they're not doing this because they have to. Oh, we got another question in the chat. This is from Udkar. I think we are just trying to treat that black hole of general relativity and astrophysical. Oh, okay. Sorry. Let me reread that. So the question is whether the black hole of general relativity and the astrophysical black hole is really the same thing. So you kind of touched on that in one of your final slides about whether what we're seeing is actually the black hole that we're predicting with the theory. So I think that's exactly what the question is here. Yeah.
Yeah, so it's a very good question, and this is something which is not obvious, but this is exactly the question, whether or not the objects that we see are explained by general relativity. So we are testing the theory with these objects, especially the gravitational wave observations. And at the moment, it seems like they completely survived the test. so they passed the test. So actually, the black holes that are, calculated in the simulations look just like the ones which are observed. So so this may be considered as good news or bad news. Of course, this is bad news because we're only finding the black holes that we already knew about, but maybe there are something else to look for. So in the future, as these instruments will improve in sensitivity, we will surely find out in more detail whether they are black holes and whether there are other things other than black holes that can be detected.
Mm-hmm. Yeah. Another thank you in the chat. Lots of thank yous. This is a really good chat. I'm sure people will be happy to be able to go back to the recording as well, especially with the last few slides that you weren't able to, spend too much time on. I don't think there are any more questions in the chat. And another thank you. We've gone on for quite a while, so I think we should end it here. Thank you again for coming here, giving your talk, and being so generous with your time. Thank you to everyone who asked questions, and hope to see you at future events. Is there anything else you would like to tell our students?
No, I'm happy that everyone came here and listened to the talk, and I encourage everyone to think about these ideas because it's an unsolved problem. There are many unsolved problems here, and we need new types of ideas which often come from young people. So I think everyone should keep this in mind.
Yes, absolutely. There's a Amelia?
Thank you so much for coming to speak with us, and thank you to everybody who watched, especially those of you who spent all this time learning about all of the ideas he had. We hope that you'll come to other events.
Brilliant. Thank you so much. Goodbye, everyone.